I just kind of want to illustrate how you can use some free technology that's available to compute Fourier coefficients of a function and actually get an abstract formula from the technology. The problem is a lot of the technology out there will give you specific Fourier coefficients, like the first 5 or 10 or so many, but to get a general formula is what we need. And we can use something like Wolfram Alpha to do this. We just have to help it out a little bit. So in the notes we had the function f of x equals x squared. I went through and kind of give you values of this. Again, remind you, I sent out an announcement. I had a typo in here. There's an extra pi floating around. I've cleaned that out. But on the notes you have still, it's still there. So please read the announcement. So this is an even function. So all the b sub n coefficients are 0 because when you integrate an even function times an odd function like sine of 5x, sine of 6x, and so on, you have an odd function which you're integrating from negative pi to pi, and that will always have a value of 0. We saw that in previous exercises. So we need to compute a sub 0, which is a very simple integral, which we have right here. We can get pi squared over 3. But for the general coefficient a sub n, we have to compute this integral, 1 over pi times the integral from negative pi to pi, x squared times cosine nx. So we can do this using Wolfram Alpha, and let me just kind of show you what I did. So we go to Wolfram Alpha, and we'll just look for integrate. Then it'll give you kind of a template for integrating functions. So the function we want in this case to integrate is x squared times the cosine of nx. And then we want to divide by pi because there's a factor of 1 over pi in front of the integral. So we can just put that in the integrand here. So we want to pick our domain of integration. So click on that. We'll set that from negative pi to pi. So we'll just type the word pi, negative pi and pi. And it'll give us a formula. No, it's somehow not liking something I did. Okay, hit the equals, and it'll give us a formula. And we'll look at the formula quite carefully here. So we can see as this kind of complicated looking thing, but in reality it's not, because Wolfram Alpha is not taking into account that n is representing an integer. It's just assuming it's some real number. When n is some real number, this is what you would get. But since n is an integer, we have this sine n pi, and we also have the cosine of n pi. Those simplify quite a bit. Sine of any multiple of pi is 0. So this entire first term of the numerator is 0. So we can just get rid of that. What's left is this 4 pi n cosine pi n. But cosine of pi n is either plus 1 or minus 1. If n is odd, it's a minus 1. Like cosine of pi is negative 1. Cosine of 2 pi is 1, and so on. So cosine of pi n can be just written as negative 1 to the power n. If n is odd, we get a negative 1. If n is even, we get a positive 1. So we can just replace this cosine of pi n by negative 1 to the nth power. And then we see that this 4 pi n times this negative 1 to the n is all divided by pi n cubed. So the pi in the numerator cancels with the pi in the denominator, and the n in the numerator cancels one of the powers of n in the denominator. So really what we have is 4 times negative 1 to the n over n squared. So we just had to help out and make those observations so that we can realize that that's really what we're getting, is a sub n is really this, but this cosine of pi n is negative 1 to the n. So I plug that in here. So we had our a0, now we're summing over the rest. So we get our coefficient our a sub n here, times the corresponding cosine function with the frequency n. And that gives us a Fourier series of the function x squared. And we'll see later that this actually represents the function exactly.